Hello. Welcome, everybody. I'm David Greenberg. This is episode 17 of the Machine Learning Seminar at HZG. We are coming from the HZG campus. We have a special guest, Anikesh Pal from IIT Kanpur, who is going to present his work on using neural networks for radiation parameterization acceleration in general circulation models. So he'll give us a bit of the background, why this is interesting, why this is important, why the radiation balance calculations are such an expensive part of climate models, and what he is proposing to do about it. Before we get started, I'll just make one brief announcement about our seminar on the mailing list. Please encourage anyone to sign up. I get people asking me, I'm not at HZG, I'm not in Hamburg, can I still join? Yes, anyone can join. That seminar is welcome, is open to everyone. So let me just introduce Anikesh. He is a professor at IIT Kanpur. He is going to show work from his postdoc in Oak Ridge National Laboratories in the last couple of years. Before that, he did his PhD at UCSD. So thanks a lot for joining us, Anikesh.
Thank you. All right, so hopefully you guys are able to see this.
Yep.
So this is
Everybody mute themselves. Yes, please mute when you're not talking, including us.
Okay, right. So I think is my screen visible? Hopefully, yeah.
Yes, okay. You're visible.
All right. Okay. So
we're starting with your notes. Yes.
Okay. All right. So so what I'm going to talk about today is how to emulate radiation calculation in general circulation models using machine learning. And here the GCM that I'm going to talk about is E3SM, which is a Department of Energy general circulation model that has been developed for a decade almost. They used to call it ACME, and now it's called Energy Exascale Earth System Model. So that's why E3SM. They have the version 1 that I ran, but I think soon it will be coming out to be version 2. So radiation is something that is very important in the general circulation model, and we are going to see, and these calculations are actually quite expensive. I'll explain why they are expensive from the next slide. And is there a way that we can use machine learning or our neural networks basically to speed up these calculations, although maintaining the accuracy that we get from the original parameterization. So this is a picture that is sort of showing that what happens when the solar radiation enters the Earth's atmosphere, right? So there are two kind of waves basically that enters the atmosphere. One is short waves, and the other one is long wave radiation. So here, as you can see, that as the solar radiation comes in, some part of it is reflected back to the upper atmosphere. Some part, transmits, hits the Earth's surface, and then gets reflected back as well. And then there are a lot of processes like this. And of course, in the atmosphere, we have different gases like water vapor, carbon dioxide, nitrogen, methane. So all of these gases play a very important role in how the atmosphere heats up, right? So what GCMs are about is, you can think of, I'm assuming that, all of you guys are really a little bit familiar with the governing equations. So the governing equations are basically the Navier-Stokes equation. Okay, so because it's fluid, but there are a lot of modeling involved in this. Okay, so if you run, say for example, a fluid dynamics problem, if you try to do it using solving the Navier-Stokes equation numerically, you can do it direct numerical simulation, or you can model the turbulence using LES. Different kind of things. But here in general circulation models, because we are not really able to resolve all the turbulence, we use some sort of modeling that can be any kind of turbulence model. Okay, but the main point here is that these are the equations, basically, which include, as you can see here, if you can see my cursor, there is a transient term, right? So del psi by del t, which is telling you that this is an unsteady process, okay, which is varying in time. And there is a d term which will actually tell you that how the advection of these entities, right? So by advection I meant that in this you have some nonlinear terms that are included. For example, if you have the momentum, you have the nonlinear terms including the velocities, right? So technically you'll write del u over del t plus u del u over del x plus v del u over del y plus w del u over del z equal to, on the right hand side, whatever you have, right? Okay, so the first term on the left hand side is the transient term, the second term is the advection term, and the third and the last term on the right hand side is sort of the forcing term. Okay, so basically these equations will solve any kind of fluid flow problem subjected to some sort of forcing. Okay, so now the same thing also applies for the energy equation as well, right? So when I say energy equation, you're solving some sort of temperature or potential temperature, okay, across the entire system or the entire domain, right? So eventually, so the first term, if psi is, say, potential temperature, so the first term will tell you the transient temperature distribution, or the unsteady temperature distribution as a function of time. The first term on the right hand side will tell you how there is nonlinear interaction, and the velocities are also included in this. How there is nonlinear interaction to determine the spatial distribution of temperature, and the last term on the right hand side, the p psi tag. So that is the forcing term. And what can be the forcing term in terms of if we are trying to look for the distribution of temperature? So as I was mentioning, the heating of the atmosphere, right? So how that our atmosphere is getting heated up, that is something that will go to go into this p psi. Okay, so which is the forcing term. So radiation is a major part which actually heats up our atmosphere, right? There are other things as well, mostly, means, as the intensity of carbon dioxide increases, these absorption will increase, right? That's what's happening, and that's why we have global warming, right? So this p psi term is a very important term when we are trying to solve for the governing equation for energy, or you can say temperature, right? Now here, as I said, p psi is a physical process in the atmosphere, such as radiative forcing, and then you have evaporation, precipitation, and a number of other things. So when I say radiative forcing, what's really happening? So as I said, initially that there will be two kind of waves that will be coming into the atmosphere. One is long wave, one is short wave. Okay, so here I'm showing another picture of this spectral irradiance. So irradiance means that how much heat is getting emitted from a particular height into the atmosphere. And this is just an example that I'm trying to show. Okay, so you can see that and these are taken from some observation. Okay, and I'll explain that what happens with the different kind of radiation models that has been used for the past years. So this is showing a spectrum of the spectral irradiance, like how much heat is getting emitted or radiated from a particular height in the atmosphere. And as you can see, there is a huge distribution, right? So you can see that the wavelength is varying from 250 nanometers to 2500 nanometers. Okay, so what this is doing, so this is at a particular height from the surface of the earth, and it's showing that the light that is getting reflected or emitted or the heat that is getting reflected or emitted is showing this kind of distribution in the wavelength, or in the spectral domain. Now, now how do we correlate it correlate this spectral radiance with this p psi, it's basically at any atmospheric level or at any height from the surface, we want to calculate the heating or the cooling fluxes. Okay, and so these heating or the cooling fluxes will actually go into the right hand side of this equation, which will be p psi, and that will determine how the distribution of the energy or the distribution of temperature, how is it going to be. Okay, sort of a forcing term. Now, to calculate these fluxes, so I have written here, two terms, as you can see here, f plus nu, f minus nu. So f plus nu means the radiative flux that is going outward from a particular surface, from a particular height. So if you divide the height from the surface um, in certain levels, so p f f f f nu plus will represent the amount of flux that is going outward, and f nu minus will represent the amount of flux, heating flux coming into the means at that particular level. Okay, now you can see, if you see this expression, you'll see a number of things here. So there is I nu mu and then mu d phi. Okay, so I nu mu, as you can see, is the monochromatic irradiance. Okay, and then this entire thing is getting integrated for all these news. Okay, so nu means you have to integrate it across this entire wavelength spectrum. Okay, and that's, so this is actually a huge calculation. So when I say, and of course you have this phi as well. Phi is the azimuthal angle, basically at what location on earth you are. Based on that, you have to do it for all of this. So you have to integrate across the entire earth as well at a particular level, of course. So these calculations are actually quite expensive. So these are integration, and when we write it in the code, we try to do, means we do it sort of as a summation, right? And the more the number of grid point in the in the horizontal direction, or the more, means higher the resolution, these calculation is actually going to become more and more expensive, because although you are adding things up, you are adding a huge number of entities, right? So this is quite expensive. And what earlier people used to do, that in line by line. So when I say line by line radiation transport model, there they used to do it for each of the wavelengths. So for example, it was 250 nanometer, then they do it for 251, 252, 253, and they will keep going like this. Okay. But later on, what happened, that when we say that we want to run it for general circulation model, we cannot do that. Although line by line calculation will give you higher accuracy, but for GCMs, they are pretty expensive to run. So you cannot do line by line every time step, right? Line by line calculation every time step. So what people came up with, and then I think I can show another paper towards the end of the talk as well. What they did was, they said, okay, what we can do is we will choose a certain interval in which this irradiance is not going to vary too much, and we'll just take an average value of it. Okay, that will speed up the process, and that's where RRTMG started coming up, and it gives pretty good results. It's not like it's not like really bad result, but it gives you a pretty decent result when we do that. So even with this part, if you increase the number of grid points in the horizontal direction, or you increase the resolution, even with that, these kind of calculations become more and more expensive. Okay, because you are doing it across the whole earth, and you are doing it in the vertical direction as well. Okay, so that becomes quite expensive. So now the idea is, we already have these models, right? RRTMG models, which people have ran multiple times. They have gathered data. So is there a way we can utilize neural networks to simplify these calculations. So as I said, there are a lot of integrations involved in this. Of course, as I said, these are summations. But is there a way we can utilize neural networks to simplify these calculations? Okay, not really these kind of integration, because neural networks are really fast to run on GPUs. There are certain advantages. It makes your life easy because they are sort of matrix multiplications. Okay, and is there any way to do it? And that was the project. Okay, when I was at Oak Ridge. So the GCM that I'll be using is E3SM, as I mentioned. What I'll do is I'll run this GCM for 1 year, collect the data, then use that data to train a neural network, a set of neural network for both short waves and long waves. And once the neural network is trained, I'm going to replace this radiation model, RRTMG model, with these neural networks and rerun it to see how accurate results are we getting. Okay, so only the training part, or building up the neural network is not enough. You have to put that model back into the GCM and run the GCM so that you know that you are actually getting the right result. Okay, all right. So machine learning, I guess everyone knows in this group that's what's going on. So we try to develop a learning algorithm with from the data, and then we test the algorithm uh, before we deploy it for the GCM. So here, just a brief that you have training images. The first row is different apples, pears, tomatoes, and then some animals, right? So you have these. When you develop a network, the network will try to um, extract some specific features of this. Then you train, you tell, so that if that's the first row, you tell that, okay, there are certain, if the apple is round, you have different textures. So when you train, you tell them, okay, this is an apple. So this is more of like you do it using convolution neural networks, or you can do it. So convolution neural network will give you much better results than DNN in some cases when you are trying to do images. Uh, but yeah, so you train it, you tell that, okay, if this is the input, this will be the output. So you have trained the model, and then you have the learned model, right? And then you give it a test case, you give it an apple, and if it will try to identify or match the similar kind of features that it has learned earlier from the training set, uh, and then it will analyze it, and if you have trained the model correctly, it should give you that, okay, this is an apple. Okay, so deep learning, as I said, is a subset of machine learning where you have multiple neural network, multiple hidden layers, where it tries to extract the data much more efficiently. Well, extract the features out of the data much more efficiently. And as I mentioned in the previous slide, that we are going to use deep neural network to see if we can really predict the radiation calculation. Okay, so here this is sort of a mathematical form that I am trying to show. So DNNs are dense linear algebra. As I mentioned, that this is basically matrix multiplication, as I'll show in a little bit. Plus, you add some bias to it, and then of course you put it in a non-linear function, which can be tan hyperbolic or rectified linear unit. And then so Py1P is the input to these networks, some non-linearity, matrix multiplication, and then some bias. You get Uy2Q, and then you go to the next hidden layer, next, and then you finally come out to the output. Okay. So here I have mentioned that these are the weights of these matrices. A and B, P, B, Q, B, R, L, B, L are the biases. And these are activation function, which will add non-linearity. Otherwise, if it is only matrix multiplication, that is simply linear. You are doing only linear operation. But as I was mentioning, that these inputs should have some non-linear relationship. That's why you need to give it a nonlinear function. So you have to pass this linear function into a nonlinear operator. Okay. So and as you can see, what's going to happen eventually, these matrix multiplications, um, using there are a lot of libraries with which using which you can really accelerate these matrix multiplication. Okay, DGEM is one of them, and nowadays you have GPUs, and then you have 2D which can accelerate this matrix multiplication tremendously. Okay, so we can take advantage of that. So that's why if we are able to simplify the radiation calculation and put it in some form like this, the matrix multiplication can be taken care of using GPUs, and it will actually accelerate these emulations. Right. So that's the idea. So this is how the neural network works. Basically, so say for example, fx is a neuron. You have some inputs as I'm showing here: 1.4, 2.7, 1.9. These are the particular weights, and this is the nonlinear function. This is the sigmoid function, as I was mentioning here, right? So this is a phi p. So you have to, once you do the linear operation, you have to pass it on into a nonlinear function. Okay, so that's what it's doing. You can see here what I'm trying to get from y1p. So y1p is this one, which is after passing these xi inputs to this operator, and as you can see, this is simply a column vector multiplied by a weight matrix. Right here, it looks quite simple because I am just doing it for one neuron, but as you'll see in this next figure, there are 3 neurons, and all of them should be all the inputs should be multiplying with all these neurons. So you'll have a weight matrix basically. I have tried to show it using different colors. I'm not really sure if the colors are visible, but so it's just basically a matrix multiplication, and then you add some bias to it, you get a number. Okay. Um, so initially we try to randomly initialize weight matrices and bias example, and then you correct everything. So here I'm giving an example that, say for example, you have an input, and we already know what the output is. Again, we have some inputs, and outputs are known. So this is a network with one hidden layer and 3 neurons in the first hidden layer. So this input will interact with all these neurons, and finally it will give you an output which is 0.9, but which is way off than the actual output, which is 0. Right. So what you try to do is you try to find the difference, or you call it the loss. Okay, and then you can do the mean squared error, and then you try to minimize this loss. Right. So you want to go as close to the output. So our output is 0 basically. Right. So you try to minimize it using stochastic gradient descent. Here is the error, right? So error basically, so first you use these inputs, you got some loss function, then you put the next input. Hello, is there? Okay, so you put the next input, you get some error. You put the third one, fourth one, you get some error, and then you add all these error, and then use this error to minimize these error to get the respective weights. Okay, and then you go do back propagation to the first hidden layer, and from the first hidden layer and to the input layer, you modify these weights, and then you go back. You keep doing this until you get a minimum error, right? So that will ensure that you have trained the network properly in this case, and then after that you say that, okay, my network is trained, it has the minimum loss, so I can use new input or unseen input and see if it actually gives the correct output. Okay, so you update weight matrices and biases using that propagation. All right, so now so that is the idea. So this is the idea of neural network, how these things work. And now I'll move on to what I have done for these radiation calculations. Okay, so now as I mentioned that for training these networks, I have to collect data, right? So now this is what we have, this is how we actually try to solve the GCMs, right? So say, for example, this is our surface. You can see the ocean, then lithosphere. So you have ocean, water, and then you have soil, right? Across the earth. And then as you can see, these boxes basically, so these boxes are the levels in the vertical direction. And then we have the atmosphere where, some radiation is, so short wave radiations are coming in, long wave radiation is going out. There are a number of things happening. And then in between you have clouds. Okay. So here it is much more clear. As you can see, this is our domain, the earth. And then from the surface, we go in the upward direction. Okay, so these are levels like 1, 2, 3, 4, 5, 6, and these are the columns, or you can call it n calls, the number of columns across the earth. Okay, I think here it is showing 3 by 3 degree, but I have taken 2-degree horizontal resolution. So each the earth is actually each 2 by 2 degree um, latitude, longitude uh, is taken as one grid, and in the upward direction, there are 30 grid points, 30 vertical levels. Okay. Uh, and then at each at each grid box, as you can see, this green box here, we are solving for the velocity, humidity, temperature. The temperature is something that will take radiation forcing, right, on the right hand side. Remember what we talked about in the first slide, right, on the right hand side of like the P psi, right? So there are a lot of other variables that we are solving at each grid level. Okay. So yeah, so I have used E3SM and I ran it for 1 year. 1 year, I mean, in physical time, not in computer time. Okay, so it will run for 1 year and it will collect the data for radiation. Now, in the next slide, I'll show what are the inputs that goes into these radiation calculations. Remember, we were talking about all these kind of integrations. So there are a lot of other things for these fluxes, the calculation of these fluxes, right? So I'll show it in the next slide, that what are the inputs that goes and what are the outputs, what are the output that these integrations gives. Okay. And that's what we need basically for these deep neural networks. Okay, so as I have mentioned here, so I have collected samples across the entire globe at each time step, so, which was also very expensive in the sense because there is a lot of it's a huge data set, around 500 GB of data that I have collected over 1 year. So this data have not only spatial variation, like across from different parts of the earth, but it's varying in time as well. So say from January to December, right? So you have all the seasons and at different locations. So you have temporal variability in the data, as well as you have spatial variability in the data as well. Okay. And I have used 5400 processors to run this entire thing. So by the way, E3SM is actually a spectral element code that is written in Fortran 90 F90. And then for the long wave radiation, I have collected 12 million samples. But for short wave radiation, it's only 6 million samples. Reason being, short wave radiations are actually active when the sun is up. Okay, so but long wave radiations are active even at night. Okay, so because the radiation will come in and then it is reflected from the surface of the earth, so it's also working at the night time. But short wave radiations are only active during the daytime. Okay, that's why the data is exactly half. Right. So and shortwave, as you'll see, that shortwave radiations have much more inputs to calculate the calculate the fluxes, not as much as long wave radiation. Okay. So now once we have these, now what I'll do is for shortwave radiations, I'll develop one set of neural networks, and for long wave radiation, I'll develop another set of neural networks. So these, now we are going to split it in two different deep neural networks. Okay. So for both of this, so if we take the long wave radiation, what I have done is I have split so this is pretty standard process. So I split the data into 90% of training data, out of which 90%, 10% will be a validation data set, and the rest of the 10% will be a testing data set. And similarly, for the deep neural network for shortwave radiation also, we'll have 90% of training data set, out of which 10% will be a validation data set, and the rest 10% will be a testing data set. Also, you want to normalize the data. So I have used a different kind of normalizations, min, max, robust, scalar, but eventually I figured out that min, max works best for this. And you want to normalize the data because, as you'll see in a minute, the output that will come out will have a huge variation, okay, in order of magnitude. So the input data is normalized, as well as the output data is also normalized. So here xi is the input data, whereas yj is the output data. So we'll normalize both the input and the output. Okay. All right. So now here I'm talking about. So this is long wave radiation I'm showing. I haven't really didn't put the shortwave radiation input and the output, but shortwave have much more inputs, as you'll see in the paper in the supplement section. I have it. So let's talk about these things. Okay, so input variables, as you can see, these are the vertical levels, right? So this is pretty standard because so when I say that I have 30 vertical levels, pressure will take one extra grid point because you have to provide boundary conditions and all of this. So that's why you have these means increased one extra vertical level. And similarly, modal interface pressure, mild dew temperature, midpoint temperature, and all of these. So these are the variables, right, that goes into the neural network. Okay, you have optical depth, and so you have different spectral bands. You want to calculate it along, and these are the outputs that you want. See here, as I was saying, these are psi. Psi was, remember in the first slide I showed that on the right hand side you have a forcing term for temperature or energy. So these are the forcing terms that you add on the right hand side of the energy equation or the temperature equation. So see, this is the heating rate, flux, okay, upward flux. So these are all kind of fluxes that you have, that we were talking about. So in the actual RRTMG or the original parameterization, these are calculated using those integrals. Okay, and those integrals have these as the input to the system. Okay, now what I have done, and this is a little bit important, and I should say that why I did this. So what I did is, say for example, level pressure is the variable 1 for all these vertical levels, right? 31. Similarly, say variable 2, which is model interface pressure, have all these at the vertical level. And similarly, say all these different variables. So aerosol absorption optical depth will have 30 multiplied by 16, right? Like a column. I'll arrange it in a column. Now what I'll do is I'll flatten it. I'll flatten it like this, so it will become a single input vector. And this single input vector goes in here in the input layer, right? For all levels, for all the variables. And if you do a cumulative addition of all this, you'll see that the long wave radiation will have in total of 1426 inputs and in total of 1154 outputs. And similarly, if you look at the supplement section of the GRL paper, you see that shortwave have much more inputs. It's around 3,800 inputs, and it will give you around 1,034 outputs. Okay. So eventually you have these flattened vectors at the input vector, and similarly at the output, you'll get these a flattened vector as the output vector as well. So you have to rearrange it according to what variable you have. So for example, you have an output, and then you know that the first 30 levels will be the long wave heating rate. Okay. So and I'm doing that because I want to create a single neural network for this. I don't really want to calculate the neural network at each vertical grid point. What that will do is so as I mentioned earlier, that these are matrix multiplication, right? So these DGEM or these libraries, the matrix multiplication libraries, they work fast if you have a huge matrix multiplication. If you try to do it at each grid level, these will be very short matrices that you have to multiply, and you have to multiply them at each grid point, and that will again will actually slow down the process. Although these are fast matrix multipliers, but if you do it for more number of times, it will require more time. So rather, if you make it as a big matrix multiplier, it will be doing it much faster. It will be doing it faster, but you are doing the calculation in a single shot. Okay, not like you're going each grid point at a single time. Okay, so that was the idea, to create such a big input to the neural network. Okay, so I take these inputs and then I train it, and then once I train it, I try to, and then we do the validation, the validation loss and the training loss goes down, and then eventually we test the data, like the 10% of the data that is left, that is never trained on or trained for the neural networks, that we test it on that. And in the next slide, I'm going to show only one sample. So one sample means, I think, yeah, so the long wave output, as you can see. So what I'm going to do is I'm only going to show one of the 10% of the data. So say, for example, I've used 12 million long wave data, right? Long wave radiation data, out of which 90% goes into training and validation, and the rest of the 10%, which is 1.2 million, is used for testing. So I'm going to show only one sample out of that 1.2 million, and later after that I'll show the cumulative error. So here you can see, it's difficult to see actually, because it gives you exactly the similar, very close result as the actual one. So there is this green dotted lines which actually falls on top of each other. And remember, I said that at one point that you have to normalize the output data as well, because see, here there is a huge variation in the magnitude. Okay, so you can see that some part it's very close to 0, then suddenly it shoots up to 250, and then there is again very small value. So you want to normalize it so that you can capture all these small values as well as the bigger values. If you do not normalize, then things mess up. I've tried it, and things mess up, and you are not really able to capture these very small values. And similarly, you can see for short waves, you have 1034 outputs, right? So this is 1034. This is for long wave, it was 1154 something. Okay, this is only one sample out of that 1.2 million that I was talking about for long wave. And similarly, this is 1 out of 600,000 samples for the short wave. But now I want to see, it's only one sample that I was looking at. But now I want to see that how much is the actual error that I'm getting when I'm predicting these values. So for doing that, what I'm doing is I'm calculating the relative error. So here I'm doing something like this. So summation of j equal to 1 to n, and then there is a modulus pj minus yj. So Pj is the predicted value, okay, which is we are getting from the deep neural network, and Yj is the actual value, and J goes from 1 to the total number of testing samples. Okay, so you take the difference between the predicted value and the actual value across all the testing samples. Okay, and then you add it, then you add all of them and then divide it by the original value for all the testing samples. And then you do a histogram plot, and this is, I think, for long wave. For the short wave, we get a similar plot. So what you see that this relative error actually stays within this 5%. So that means we are able to achieve around 95% of the accuracy, right? Or around 90 to 95% of the accuracy in predicting these variables for the long wave and the short wave. Which is quite good actually. It means so it appears that DNNs are efficient in calculating this. But you know what? This is just developing the deep neural network. So the story doesn't end here, because if I just report this, people might ask that, okay, it gives you the thing for when you do it for a single year, right? But remember, when you are running it into the GCM, the original parameterization is running into the GCM. At every time step, if you try to implement these DNNs into the GCM and try to rerun it, does these errors actually increase? Okay, and well, the answer is not, because you'll see that in the next few slides that we get very similar results with the original parameterization, with the fact that we speed up the process by around 8 times. So the DNNs are implemented in the climate model to replace the original radiation parameterization, and we repeat the simulation for 1 year. Okay, so here are the results. So this is what I'm trying to show here. This is the surface shortwave flux and surface long wave flux. This is at the surface of the Earth, and these are annually averaged. So annually averaged means we have averaged over the entire year, right? And then we see that what is the variation, and you can see that the distributions are quite similar. So the first, this figure is using our deep neural network, and this is for the first year, and this is for the original parameterization. So you can see that the mean is around 159, and we are getting around 161. So which is a pretty good match. And similarly, for the long wave surface flux, you can see this is around 50.87 from the DNNs, and here we are getting around 54.7. That is the sort of the mean, but you can see that the distributions are quite similar among these two. Okay, so yeah, so that means that the DNNs were actually able to predict these surface fluxes quite efficiently. Okay, so these, remember, this is still, I'm talking about the fluxes, right? So and our original goal was to predict these fluxes that goes into the right hand side of that governing equation, right? And then DNNs also accelerate these calculations by 8 to 10 times. Now I really haven't shown it here, but I think in the paper it is somewhere there. So the reason it gets faster is because, as I mentioned, that these are matrix multiplying calculation, right? DNNs are basically matrix multiplication plus one bias addition, and then you just put it into a nonlinear function, right? But matrix multiplication is the part that we are most concerned with, and as I said, DGEM is one of the libraries that does it much quickly. And as the bigger your input vector is, or the bigger your matrix multiplication is, the less time it will take, because that it is designed like that. So what it does, it is because of these matrix multipliers that this calculation becomes faster. Another thing is, which we figured out after the paper got accepted, we have reduced the number of floating point operations when we use DNNs instead of the original parameterization. On the top of my head, I don't really remember what was the difference, but the number of floating point operations that I was using in the DNN parameterization was much less than the original parameterization. So that also speeds up these calculations. Okay, so that's why we have around anywhere between 8 to 10 times from long wave to short wave. And the way I calculate these 8 to 10 time calculation is basically you take the CPU time from each of the processors, so 5400 processor, and you sort of average what you get for the original parameterization and DNN, and then you compare. Okay, so here, okay, so after this there are some line plots actually which I wanted to show. So now these are zonally averaged, zonally and annually averaged. So you average it across all the seasons or all the months or for a year, and then you average along these longitude. Okay, so if you do longitude, it's zonally averaged, and then of course you plot it across this latitude. You have 0 and then 30 south, 90 south and 90 north, and you can see here that this is surface. This is one of the variables again. That this is downwelling surface shortwave flux, and you can see that this average value is also actually quite similar. So DNN are able to predict what we have for the parameterization. So the red dashed line is from the original parameterization, and the dark black line is from the is predicted from the deep neural network. Similarly, for the long wave downwelling flux, you can see that there are certain variations, but overall, you get a very good match towards the 90 south. There is little bit difference, but these differences are not really that much. If you plot the difference plot, you'll see that this goes up to around 220, and this difference is around 8 to 10. So it's around 90% accurate. So there are other variables as well, radiative fluxes, which I did not really show, but they also give you quite similar accuracy. Now, remember here we were talking about only the temperature fluxes, right? I mean the heating fluxes, cooling fluxes. But then these fluxes are the forcing term on the right hand side of the governing equation for the temperature or the energy. But then these temperature is actually coupled with a number of things, like one of the variables that it is coupled with is the precipitation rate or humidity, you can call it. Right? So if our radiation fluxes are calculated accurately, which means our temperature distribution is calculated accurately, and if the temperature distribution is calculated accurately, then as it is coupled with the humidity or precipitation or other scalars, active scalars, they should also show accuracy, right? So to check that, for the prognostic variables, so I have plotted here the precipitation rate, and this is also annually averaged, and you can see that the variation is quite similar. And similarly, I have shown a zonally averaged one, and once again, these are the DNNs, because of the radiation parameterization using the DNNs is correct, we are getting quite close distribution of the of precipitation rate as well. So I think so. Yeah. So that was all about this paper. So here with this, I would like to conclude what I have done. That DNNs are capable of providing accurate prediction for radiative fluxes for E3SM, and I think there are now more and more attempts of predicting radiative fluxes, more advanced radiative transfer calculation using RRT MGP that can be implemented in GCMs for more higher accuracies. And of course, the deterministic and prognostic variables, as I said, the prognostic variable here was the precipitation rate that I have shown, but the velocity, the wind velocity, and all the things, all the other things also matches. Well, it's just I haven't shown it here. Which is sort of coupled with the energy equation or the temperature equation, where the radiation fluxes are playing a major role on the right hand side, as the forcing term also match well. We were able to accelerate these radiative computation by around 8 or 10 times because of less floating point operations used by the deep neural networks. And of course, the matrix multipliers are done much quickly using this DGEM library. And that increases our accelerate this calculation by 8 to 10 times, although we are getting around 90-95% of accuracy in their calculations. And so this remains an open question, because now you'll see that there are a lot of papers on artificial intelligence assisting in different kind of computation, especially in radiative calculation. So so the open question: can this become an integral part in future computational techniques? So I would like to thank you all for listening, and I'd be happy to answer any questions.
Thank you so much, Anikesh. We can take questions from the chat or from the YouTube stream if we have any. I want to start off asking a slightly technical question.
Okay.
Which is, so you train this network in Keras, and it's great. You trained Keras TensorFlow code. You shared Keras and TensorFlow code.
Yeah. I forgot to mention this. Yeah, I have used TensorFlow. Well, Keras, which is a wrapped, which basically uses Google Tensor.
Yeah. So my question is, I mean, you train this in Keras, and then you have to deploy it inside of a Fortran GCM.
Correct.
So how difficult was this process of deploying the trained network inside the GCM, recompiling it and getting it to run? And do you have any tips for someone who might want to do this?
Yeah. So let me tell you this. So I probably have skipped that part. So when you train these networks, eventually after training, what do you get? So we get the weight matrices, right? And the bias matrix, right? So here, let me go back to this. So this, let's say this slide, right? So after training, when our losses are minimized, eventually what we are going to get is these weight matrices, right? And these bias vectors, right? So what it will do is, what you can do, so Keras is, you train this on Python basically. So eventually what you get is these weight matrices, and these weight matrices, you can, once you get it in Python, you know the elements, right? What is this weight matrix? You can form it in a Fortran array. Okay, so for this weight, so like it will be a 2x2 matrix, but it will be a bigger matrix depending on the number of neurons you have. And the bias vector will be a single column vector, right? So you rearrange them in Fortran, right? In arrays. You take this, you put it into the code. Okay, you read it once. You just have to read it once, because it's in the beginning of the, when you start or initialize the code, you just read it once, and then you just put it in the radiation calculation where you have to do this matrix multiplication. You did BGM. But to answer your question, it was initially I struggled almost around 1 to 2 months for this. Reason being, so this code, E3SM is quite complicated code. So I have a very advanced, worked on very advanced Navier-Stokes solvers, but E3SM is sort of one of the most complicated codes that I have ever seen. Reason being, there are a lot of arrays that you call, and then there were a lot of bugs that I have to keep debugging for almost a month and month or two to implement it back into the code. But I was able to do it. So the advice to some people who are actually trying to do it is patience, and you have to keep rerunning it. And my code, eventually, first time when I wrote it, the code crashed. And then you look at the log file where it is crashing. You keep doing it until it works, until it gives you the correct matrix multiplication. Or what you can do is you can write a standalone Fortran code where you want to do this matrix multiplication. You give some of the inputs of your own that if you take a vector, you multiply it with this weight matrix and add the bias vector. Are you getting the same thing that you are calculating by hand? So I keep doing that, and eventually, when the standalone model looks like it's working, then put it back. So there are a couple of techniques, or there are a couple of things that I tried, and after struggling for almost 1.5 months, 1 or 2 months, I was able to do it. So the code is running smoothly, and then eventually it gave results.
Thanks. We have a question from the chat from Carolina Arnold from DKRZ. She's asking, how does a DNN generalize? For example, if you train the DNN on 1 year of data from the parameterized model and use it for predictions in the second year, how accurate are these predictions compared? And let me just add on to that. When you broke it into testing and training data, did you pick one section of time for testing, or did you just pick them randomly from different time points?
Okay, so to answer first your question, David, no. So I did it randomly. I did not really pick a single set of time. So if I try to do, I just pick, like, say, for example, if I train from January to March at certain location, okay, so say towards means in North America, right? It would be much colder, so that part will only be taking into account the winters, right? But in the southern hemisphere, it will be summer, right? So we cannot really just train it at a certain location and at a certain time. You just do it randomly. You just pick it up random, because now your data sets have these are arranged into giant vectors. Like as I said, for the longwave it was around 1400 something inputs. So now you just pick up, after this means after rearranging all of this, it's just a simple DNN training. Okay, so you do not really just pick one time means at a single means as a period of one particular time instance or one particular region. You want to do it randomly so that your network is trained on different in spatially variable and temporally varying data. To answer Caroline's question, so now if you see the paper, actually this DNN works really good for the second year as well. Okay, and I have ran the DNN and the original parameterization for the second year as well, and you can see that the internal variability still is around 8 to 10%. Okay, not more than that. But what happens, and I have ran this DNN for the third year as well, it works fine. But from the fourth year, it starts sort of giving diverging result. Okay, so there is a reason for that. The reason is the data that I have used is only for 1 year. Right, that sort of, so initially what we were trying to do, and as you can see, these were sort of quite expensive computation. So 1 year data, as I believe, is very short period of time to train your neural networks. So if you just train it for 1 year and you want it to give you a prediction for the next 10 years, means that really cannot happen. Okay, because within a period of a decade, there are a lot of temporal as well as spatial variability. So Now, to generalize these networks, you might have to run it for a longer time to collect the data and then train your neural network based on that huge amount of data. Okay, so that is expensive business, and my term sort of ended in Oak Ridge, and I left and I joined here. But there is a student who is actually working on this. So what Lindsay, she is still there. What she is working on that instead of doing 2-degree resolution, which is still 100 kilometer by 100 kilometer, which is still relatively fine grained. So what she have done, I think she have done 4-degree resolution, and she have ran it for 10 years. And now she is trying to train a neural network for over a decade. And then we can see that if it is able to predict everything for the next decade or not.
Okay, thank you. So this answers also another question that was just asked in chat of what would happen if the GCM grid were finer. I guess we'll find out when we see those results when they're published in some time. I think we have time for one more question, again from the Zoom chat.
Okay.
So the question is, how would this generalize to a different context where maybe the CO2 is much higher?
Yeah. So that is also something that that has not. So as I said, it's not really. It was not really a generalized deep neural network because of the fact that I have only used 1 year of data. Okay. Of course, based on this initial condition, that is actually a good question. Like, what happens if you have twice the carbon dioxide, if it is able to give you accurate results as you have with the original parameterization. But that is like, you have to initialize it earlier, that if you have twice the amount of carbon dioxide. I haven't tried that, and that is actually something good, and maybe this can be passed on to the people in the Oak Ridge if they want to try that. But I haven't really tried using it for a different context.
Okay.
But of course, that is a good question. I mean, of course, that should, if it is at least generalized for 1 year, it should at least give you, I would say around 80 to 90% of accuracy. But I'm not really sure. I'm not really in a position to answer that question. But hopefully that in the next paper that we are writing, sort of after that, maybe we can try this.
Okay, thanks a lot. Thanks for explaining this stuff. This is a really interesting topic. It seems to be developing very quickly. I wonder how long before we'll really see neural networks used in operational climate models, and maybe in some of the next predictions we'll really see them become a standard tool. So this is really exciting work. Thank you again for joining us.
Yeah, thank you so much, David. Thank you all.
Thanks, everyone. See you in 2 weeks. Bye-bye.